Welcome to today's paper reading. Today's paper is titled, Photon Inhibition for Energy-Efficient Single-Photon Imaging. This paper was published on AR14 by Lucas J. Koerner and colleagues from the University of St. Thomas and University of Wisconsin-Madison. Single-photon cameras, particularly those based on the single-photon avalanche diode, SPAD, are increasingly being used in challenging imaging scenarios. These cameras detect individual photons through an avalanche process, which allows for the extraction of scene information under conditions of extremely low light, high dynamic range, and rapid motion. However, the energy consumption per photon detection in SPADs is higher than in CMOS cameras, which limits sensor resolution and could hinder the widespread adoption of SPAD-based single-photon cameras. To address this issue, the authors propose a computational imaging approach called photon inhibition. This method strategically allocates photon detections in space and time based on the goals of the downstream inference tasks and resource constraints. The authors develop lightweight, on-sensor computational inhibition policies that use past photon data to disable SPAD pixels in real time, thereby selecting the most informative future photons. Through case studies focused on image reconstruction and edge detection, the authors demonstrate, via simulations and real SPC data, a significant reduction in photon detections, over 90%, while maintaining task performance metrics. This work raises the question of which photons should be detected and paves the way for future energy-efficient single-photon imaging. Photon inhibition is a technique where individual SPAD pixels are selectively disabled to reduce energy consumption while maintaining performance in various computer vision tasks. This method involves lightweight computations called inhibition policies, which determine in real time which pixels to enable or disable based on previous photon detections. These policies are inspired by the human visual system's retinal processing. The approach also introduces novel energy-aware imaging performance metrics to optimize for signal-to-noise ratio and specific vision tasks, thereby reducing the overall detection energy. Figure 1 illustrates the concept of photon inhibition in single-photon avalanche diode, SPAD, imaging for resource efficiency. In Part A, it is shown that unlike conventional CMOS cameras, the energy consumption in SPAD cameras escalates with the brightness of the scene, which severely restricts the use of high-resolution SPAD cameras in applications with limited resources. Part B introduces the expansion of the conventional imaging pipeline to include inhibition, a process that electronically enables or disables individual pixels to manage bandwidth and power usage. This method is supported by lightweight mathematical operations termed inhibition policies, which adjust inhibition patterns based on the history of photon detections. These policies can be tailored to optimize image signal-to-noise ratio, SNR, or cater to specific downstream vision tasks. Parts C and D demonstrate that object detection, a high-level vision task, can still be effectively performed even when a substantial fraction of photons are inhibited. The power consumption of SPAD sensors is heavily influenced by the pixel size, with smaller pixels reducing the avalanche energy. However, even with recent technological advancements, avalanche energy remains a significant portion of the total power consumption. Various design optimizations, such as RF modulation of the bias voltage and minimization of junction capacitance, have been implemented to reduce the charge per avalanche. Additionally, SPADs require recharge after detecting photons, a process known as dead time, which can inhibit the detection of subsequent photons at high exposure levels. Clocked recharge methods have been developed to reduce power consumption during high photon flux by limiting the number of detections within a recharge period. Furthermore, resource-aware imaging techniques, such as event-based vision sensors, have been employed to reduce power consumption by selectively disabling photodiodes based on photon history, focusing on passive imaging scenarios with computational constraints. In the observation model, the photon flux phi during an exposure time t results in an average exposure h equals t. The effective flux phi incorporates the sensor's photon detection probability, PDP. The distribution of photon conversions follows a Poisson distribution. For SPAD pixels, the readout in each binary frame is a Bernoulli random variable b, with a probability y equals 1 minus e minus h of detecting at least one photon. Multiple measurements are taken to reduce noise, leading to a total number of detections d that follows a binomial distribution. When inhibition is applied, represented by a binary state variable m, the number of measurements and detections change accordingly, still following a binomial distribution. The traditional metric for evaluating single-photon sensor performance is the exposure-referred signal-to-noise ratio, SNRH. This is calculated as the ratio of the true exposure h to the root mean squared error and the estimated exposure. At low incident flux, SNRH is low due to shot noise, but it improves as the likelihood of photon detection increases. However, in bright light with H greater than 1.6, SNRH degrades due to the soft saturation of the sensor response. To address the energy costs associated with SPAD sensors, two new energy-aware modifications to SNRH are proposed. The first is a detection efficiency metric, SNRH superscript 2/d, which is defined as the square of SNRH normalized by the expected number of detections. This metric increases linearly when h is much less than 1, indicating significant information contribution from all detections. The second metric is measurement efficiency, SNRH superscript 2/w, which normalizes the square of SNRH by the number of measurement windows. This metric shows suboptimal efficiency at both low and high exposures, with the best efficiency occurring at h equals 1.59 and y equals 0.80. The proposed policies calculate a spatiotemporal inhibition pattern for each pixel and frame. This is defined using a binary value tensor m, where m, I, j, t equals 0 if the pixel, I, j, is disabled in the TTH frame, and m, I, j, t equals 1 otherwise. The binary photon cube, f, is defined similarly, with f, I, j, t equals 1 if the pixel is enabled and a photon is detected. The inhibition score, S, is calculated using a spatiotemporal filtering kernel, K, and compared to a threshold eta to determine if the pixels should be disabled. Figure 2 illustrates the concept of calculation-based inhibition with dead time. The arrows represent incoming photons, with an X marking those that are inhibited. The letter T indicates the clocked recharge period, during which the sensor is recharged and ready to detect photons again. The key feature of this inhibition method is the score S, which is calculated based on the history of photon detections in past frames. This score determines whether future measurements are enabled or disabled, thereby managing the photon detection process efficiently. Figure 4 illustrates the concept of saturation look-ahead inhibition in single-photon imaging. In Part A, the inhibition mechanism is described where if the detections in cycle I exceed a specified threshold, the photons arriving in the subsequent recharge cycle, I+1, are inhibited. This is demonstrated with thresholds D1, D2 set to 3, 3. Parts B, C, D provide examples with different recharge period settings and measurement brackets, showing how the saturation thresholds D1, D2 equals 7, 7 are applied. The brackets are linearly combined, weighted by SNR2, demonstrating that this approach has a negligible effect on the reconstructed SNR compared to conventional clock recharge methods. Notably, this inhibition policy results in significantly fewer photon detections in high-flux environments. In Part D, it is shown that individual brackets are effectively disabled in low detection efficiency regimes, with the detection rate closely following the original SNR2H curve. Detailed simulations supporting these findings are available in the supplement. The authors employ Monte Carlo simulations to generate sequences of binary frames from RGB images. These simulations are used to evaluate various inhibition policies, including those that extend the baseline inhibition generated by clocked recharge. The performance of these policies is assessed by calculating inhibition scores and patterns. Additionally, the authors developed spatiotemporal policies that combine 3x3 spatial kernels with a 4-length temporal kernel to enhance image reconstruction. For edge detection, the BSDS 500 dataset is utilized to study energy-efficient edge detection through photon inhibition. The results show a 30% reduction in detections on single exposure time captures, demonstrating the effectiveness of the proposed policies. Figure 5 illustrates the power-efficient static imaging achieved through inhibition policies. The figure showcases images from an exposure bracketing sequence with average exposures of 0.1, 1.0, and 10.0 photons per pixel, ppp. Panel A. Contrast images generated using clocked recharge with and without inhibition. Panel B displays the distribution of measurements based on pixel intensity at 1.0 ppp. Panel C evaluates image quality using the Structural Similarity Index measure, SSIM, at equal detections per pixel. Panels DG present the results of testing handcrafted inhibition policies over 20 images, focusing on reductions in detections at equal SSIM. The top row DE employs exposure bracketing, while FG uses a single exposure of 1.0 ppp. The box plots in D, F, and E, G show quartiles with the median line, indicating the performance of the proposed policy, PCR, which uses a 3x3 spatial kernel emphasizing the center pixel and its neighbors. Panel H summarizes the average inhibition patterns for each exposure time, demonstrating that the brightest pixels are inhibited the most, especially in the sky, while the longest exposure time primarily allocates measurements to the darkest pixels. Figure 6 illustrates the effectiveness of inhibition in energy-efficient edge detection. The graph shows the F-scores of edge detection averaged over 19 images plotted against the average number of detections per pixel. Horizontal arrows indicate the reduction in detections achieved through inhibition while maintaining equal task performance. Notably, at and beyond 30 detections per pixel, the performance of inhibition and no inhibition becomes nearly equivalent, plateauing at 200 detections per pixel. The edge detector achieves an F-score of 0.813 on the original images, highlighting the potential benefits of inhibition in reducing detection counts without compromising detection quality. In dynamic scenes, significant motion is present even with the high frame rate of a SPD camera. Burst reconstruction algorithms are used to yield high-quality images from sequences of binary frames. The study focuses on the saturation look-ahead policy, an adaptive single-pixel temporal policy. To avoid losing salient information under motion, the inhibition policy limits extended dead time periods. The experiments use a Fibonacci bracketing sequence and convert each bracket to a maximum likelihood estimate of flux. The results are obtained using the Swiss SPAD-2 sensor, which captures binary frames directly, and inhibition is emulated in software. Figure 7 illustrates the effectiveness of adaptive inhibition policies on video sequences. In Part A, burst reconstructions for 3 keyframes under varying light levels are shown. The top and bottom rows differ by approximately 7 stops. The left column displays results from the original binary frames without inhibition, while the right column shows results after subsampling 10 times, representing a fixed 90% inhibition. The middle column demonstrates exposure bracketing combined with saturation look-ahead. Under strong light conditions, top row, both methods yield reasonable results. However, plain subsampling loses details in lower light, as seen in the middle and bottom rows, where the furniture and a person's outline are less distinct. Adaptive inhibition, on the other hand, is more effective in preserving details by being adaptive to flux. Part B presents the average exposure level for each keyframe in the sequence. Parts C and D show per keyframe and cumulative detection counts, respectively, indicating that inhibition results in fewer photons being detected over the entire sequence. Part E illustrates the number of measurements taken for each keyframe, suggesting potential energy savings during readout due to reduced measurements. The plots in C, D, E are subsampled for clarity, with crossover points marked by green arrows. The paper focuses on reducing energy consumption due to avalanches, but acknowledges the need for a holistic model that includes computational and readout energy. The computations in the model are designed to be lightweight, leveraging recent advancements in computational SPD imagers. The current noise model only accounts for photon Poisson noise and quantization noise, and future work should expand this to include practical sensor limitations. To generalize the approaches to various vision tasks, task-specific quality metrics need to be defined for optimization, as demonstrated with the image reconstruction task using the MSE metric. The authors would like to express their gratitude to the Minnesota Supercomputing Institute at the University of Minnesota for providing essential resources. Additionally, AI received partial support from the NSF ECCS 2138471 grant. SG and MG were supported by multiple sources, including the NSF Career Award 1943149, the NSF Award CNS 2107060, and the Wisconsin Alumni Research Foundation, WARF. These contributions were crucial for the successful completion of this research. Thank you for watching.